Welcome back. Today we'll discuss the topic of what is known as polynomial division, otherwise known as chapter 5.5 in your textbook. Last week, we learned that one can divide a monomial represented by, say, a raised to the m by another monomial, such as a raised to the n. And what you do is you can actually just subtract the exponents between the two monomials. And so, in a very limited manner, we can say that we do know what happens when you perform polynomial division, because if you had, say, x to the seventh divided by x to the fifth, we can say without equivocation that all this is going to be equal to would be that you're going to take x and you'll raise it to 7 minus 5, which gives you x to the second power. So we know that x to the seventh divided by x to the fifth gives us x to the seventh power. The question that we're going to answer in class today is, what happens if you take a more complex polynomial? Maybe complex isn't necessarily the best word choice, but a more complicated polynomial perhaps, and you divide it by another more complicated polynomial expression, something like 9x cubed minus 21x squared all over 3x. What happens here? Okay, if we back up to the case of dividing a monomial by another monomial, you'll recall that one of the reasons why this monomial obeys the exponent subtraction rule in the first place is that what's happening on top is you've got x multiplied by itself basically 7 times, and on the bottom you've got x multiplied by itself 5 times. And then what happens here is that by composition of fractions rule, which if you guys recall, if you have it a times b all over c, this could be rewritten as a over c times b. Okay, so by the composition of fractions rule, you can start breaking open this big fraction by writing x divided by x on the top and the bottom, and you'll have what are effectively 2 x's left over, and then your x's will divide out with each other. So we'll have just x times x, or x squared. Okay. The first thing that we should know about polynomial division is that if it's possible for us to divide one polynomial by another polynomial, what is going to happen whenever we go about reducing these polynomials is that we are going to be acting in such a way that will be very, very similar to an ordinary division process. And what we mean by ordinary division process is that if you have, say, 100 divided by 10, what we learned before is that because we can write 100 as 10 times 10, then you'll have 10 times 10 divided by 10. And because there is what is known as a common factor in the numerator and denominator, the common factor essentially divides out. And so one way to approach these problems is we need to determine if there is such a thing as a common factor with the numerator and the denominator. Okay, and so this introduces what is known as the GCF technique for polynomial division. Okay, so what we're going to do for 9x cubed minus 21x squared is just like with this 100 divided by 10, we can essentially try to determine if there is a GCF that exists in common between one or more terms in our numerator. And if the GCF is in common with the numerator and the denominator, then terms will start to divide out. And so how this works is you can actually go to the side of your page,
say, take your 9x cubed. And what you want to do is you want to find all of the numbers that divide the term 9 that's out in front of your x cubed. And so, of course, you would say, well, 9 is the same thing as 3 and 3. And then similarly, you can try to find all of the terms that divide x. So, or rather, x cubed. And you would say that x cubed is the same thing as x times x times x. And so you can rewrite this 9x cubed as 3 times 3 times x times x times x. And similarly, you can take the 21x squared, and we can rewrite 21 as 7 times 3, and x squared as x times x. So now you have 7 times 3 times x times x. And at the moment, it seems as though we're just kind of breaking up these terms and making everything more complicated. But here's the trick, guys. What the GCF technique is going to allow us to do is this is actually going to allow us to simplify this fraction if it's possible to do so. And what we're trying to look for here is we're actually trying to look for terms that are in common between the 9x cubed, or the 3 times 3 times x times x times x, and the 21x squared, or said another way, the 7 times 3 times x times x. And what you'll see is that you've got a 3 times x that's in common between both of these terms. And so what's interesting is that if you guys recall the distribution law, whenever you have a term that's multiplied out in front of the sum of two or more terms, you know that you can essentially take the term that's out in front and multiply across the sequence of parentheses. What we're doing here is we're actually going in reverse. We're trying to figure out if there's a term in common, and then we will rewrite this as a product of the sum of two or more terms. And so we've got a 3 times x that's in common. And then what we're going to do is inside of parentheses, we're actually going to write what is left over. I've got a 3x and 7 that's left over. Okay. Now you can simplify this if you want to, but for the moment, it's probably best if we just leave our terms in the expanded notation. And what we're going to do is we're going to recall what we're actually trying to do in this instance, and that is we are trying to calculate what 9x cubed minus 21x squared all over, what was it, 3x, is equal to. What is this equal to? Okay, so what we've done now is we have attacked the numerator. And what we found is that the numerator is equal to 3 times x times 3x minus 7. That's all over 3 times x. So the pattern, guys, is just like before where we had 100 divided by 10, and you can expand out 100 into 10 times 10 over 10, and that gives you 10. When we expanded out this numerator, what we're ultimately trying to look for is we're looking for terms that are common between the numerator and the denominator. And so you'll see that you've got an x and an x, a 3 and a 3. So this is going to give you x times the quantity 3x minus 7. And of course, by distribution law, you can go ahead and multiply across, and you'll get 3 times x minus 7 times x. Or said another way, you'll get 3x squared minus 7x. And that is your best answer. All right. Now, there are a couple of hiccups that we need to understand whenever we're actually going about doing polynomial division. First hiccup is if we back up to this step right here, I have seen a fair number of students who even in Math 1050 or Math 1100, they'll ask the question, look, if we have 3 times x times the quantity 3x minus 7, why can't I just like divide out the 3x and the 3x there? Why can't I do that? Right? Why can't we? And the issue is that we have to be very, very careful when dividing out quantities that are in a sequence of parentheses, because what's happening is you can violate the distribution and or associative law very, very easily with these types of problem statements. And so basically, when you've got 3 times x times 3x minus 7 over 3x, what we need to remember is that by the rules of fractions, this is the same thing as 3 times x on top over 3x. And then you've got this 3x minus 7 parked out in front. And so while we can essentially simplify this quantity on the left-hand side and we'll be left with x times 3x minus 7, it's not necessarily the case that we could, it's not the case, actually, it's not the case that we can just divide out the 3x and the 3x terms. And another way of thinking about that is, suppose you have a problem statement such as 120 minus, we'll say 10 over 20. Okay, so suppose you've got 120 minus 10 over 20. And a student would say, look, I know 20 goes into 120. Well, 20 times 5 gives me 100. 20 times 6 should give me 120. So I should be able to just divide out the 20 into 120, and that would be 6. So now this is 6 minus 10, and that would give me negative 4. But the problem here is that what you're doing is you're violating the distribution law, because what is actually written is you have 120 minus 10 times the quantity 1 over 20. Okay, remember that division is the same thing as multiplying by an inverse. So when you've got 120 minus 10 divided by 20, it's the same thing as having 120 minus 10 times the quantity 1 over 20. And so by the distribution law, what's actually happening is you have to distribute this 1 over 20 to each of your terms. You'll have 120 times 1 over 20 minus 10 times 1 over 20. And so at this point, yeah, you would have 120 divided by 20, and that would indeed give you 6. But the adjustment that you would have to make in order to do that dividing out operation is that you would have to also take your 10 and divide it by 20. And of course, there, 10 divided by 20 just gives you 1/2. And so 6 minus 1/2 gives you 5.5, or 5 and 1/2 if you like. So your true answer should be closer to 5.5 as opposed to -4. And you only got to -4 because you violated the distribution law. And the same thing would happen here above. We really, really need to be aware that, by the distribution law, if you have something like 3x minus 7 all divided by 3x, and mind you, I realize that that's not what is actually written there, but supposing you had 3x minus 7 all divided by 3x, the reason why you can't just, or another reason why you can't just divide out these terms with one another is simply that this is actually the same thing as 3x minus 7 times 1 over 3x. And so what would happen here is that you have to distribute across each of these terms. You would get 3x times 1 over 3x minus 7 over 1 over 3x, just like that. Okay, and yes, the first term would divide out. You'd have 3x divided by 3x, which would give you 1. But then the second term would be a 7 over 3x. And of course, you can't really divide 3x into 7, so that would not disappear. There would be nothing you could do with it. That would just be your answer, just like that. Okay, and this brings us to the second technique that the book teaches in terms of how one can handle the division of a polynomial by a simple polynomial. In this case, we have a simple monomial expression 3x that's dividing into a more complicated sequence of terms. In this case, a binomial 9x cubed minus 21x squared. One of the techniques that the book teaches is that we should just treat this as though we are multiplying by an inverse, which is all well and good. So what the book is going to show is it says, look, if you have 9x cubed minus 21x squared, and you're trying to divide by 3x, doesn't exactly explain it this way, but here's what's going to happen. You're going to take the 9x cubed minus 21x squared, and we're going to pretend that we are multiplying with a 1 over 3x. And so when we multiply these terms, you're going to have a 9x cubed times 1 over 3x minus 21x squared times 1 over 3x. You'll get a 9x cubed over 3x, 21x squared over 3x. And at this point in time, you can expand your 9x cubed, just as I had done previously, where you would say, okay, well, 9x cubed is the same thing as 3 times 3 times x times x times x. This is over 3x minus 21x squared is the same thing as 7 times 3 times x, all over 3x. And basically, at that point, you'd start dividing out like terms. Your 3's would divide out, your x's would divide out, and you're going to be left with 3 times x minus 7 times x, or 3x squared minus 7x. So that is the second way that you can perform polynomial division. So the first way would be to expand out everything and then divide out like terms. I think that otherwise known as using the GCF technique to simplify a polynomial expression is a pretty easy and or familiar way to simplify a polynomial. But the second way would be to just use the distribution law and then try to find or divide out like terms between your numerator and denominator for however many polynomial expressions you may be dealing with. So in a slightly more complicated example, we work problem 17 from the textbook. We have 5n to the fifth minus 10n cubed minus 25n, and this is going to be divided by 25n. If we were to use the GCF technique in the numerator, you're going to have 5 times n times n times n times n times n minus, because n to the fifth is going to be just n multiplied by itself 5 times, minus 5 times 2 times n times n times n, minus 5 times 5 times n. That'll all be in your numerator of your expression. And then in your denominator, you'll just have 5 times 5 times n. All right. So what's going to happen here is we are looking for terms that are in common in the numerator of your expression. You'll note that you have a 5n in common with all of these different terms, which is great because in your denominator, you can also see that you've got a 5n in common. So if you take out the 5n, you'll be left with n times n minus 2 times n minus 5 on top, all over 5 times 5 times n on bottom. If we remember that we cannot divide out terms that are inside of our parentheses, and we only focus on terms that are outside of the parentheses, you can divide out a 5, you can divide out an n. So you've got in the inside of your parentheses an n to the fourth minus 2n squared minus 5. All of this will be multiplied by 1 because 5n divided by 5n just gives you 1 all over 5, and 1 times anything is just that something. So you can even, when you get comfortable with this, skip this step. You'll just have n to the fourth minus 2n squared minus 5 all over 5, and that's your answer. That's pretty much all there is to it. Now, personally, I think the GCF technique is easier to use than distribution, but regardless of what the student decides to do, you're going to be left with this roughly the same number of steps. So if we go back and we try using distribution for this problem statement, we've got 5n to the fifth minus 10n cubed minus 25n all over 25n. And by the distribution law, we know that that's going to be 5n to the fifth minus 10n cubed minus 25n times 1 over 25n, or the inverse of 25n. And then we're going to distribute this 1 over 25n to all of the terms inside of our parentheses using the right-handed distribution. So we've got 5n to the fifth times 1 over 25n minus 10n cubed times 1 over 25n minus 25n times 1 over 25n. Oh my goodness, now we have to deal with a bunch of fractions. That's kind of a pain, but we got this. We get 5n to the fifth over 25n minus 10n cubed over 25n minus 25n over 25n. All right. 25 cancels out, n cancels out. You just get 1 n cubed minus n. That's just going to give you n squared. 10 divided by 25, well, 5 goes into 10 2 times. 5 goes into 25 5 times. It's going to be a minus sign. 5 divides 25 5 times. 5 divides 5 once. And n to the fifth divided by n goes into the fourth. So you get, we clean this up a bit, we have 1/5, whoops. And this is going to look a little bit different than our previous answer, but it's actually the same thing. Minus 2/5 n squared minus 1, and that is also our answer. So if fractions don't bother you, then using the fraction rules in order to multiply out the product of 5n to the fifth minus 10n cubed minus 25n with 1 over 25n might be the way to go. All right. There is, in fact, a final technique that we should consider whenever we're approaching these polynomial division type problems, and that is what is known as polynomial long division. Okay. So with polynomial long division, if we back up to the first example problem, say we wanted to, calculate 9x cubed minus 21x squared all over 3x, and we wanted to know what is this equal to. With the polynomial long division technique, what we are going to do is very, very similar to long division. So if you guys recall how long division works, suppose you wanted to, I don't know, divide 257 by 2, and I wanted to calculate what this is equal to. Using long division, what you do is you place your 2 out in front, and you're going to ask yourself how many times 2 goes into 257. Well, 2 goes into 2. 2 goes into this first term, 2, this first digit, 2 one time. And then the pattern is you then take the 1 and you multiply, you back multiply with the 2. So 1 times 2 gives you 2, and you subtract the resulting quantity. 2 minus 2 gives you 0. At that point in time, you drop the 5 down. So then you ask yourself, how many times does 2 go into 5? Well, 2 goes into 5 2 times. 2 times 2 gives you 4. Subtract. 5 minus 4 gives you 1. Drop down your 7. 2 goes into 17. Let's see, 8 times. 8 times 2 gives you 16. Subtract. And you get a remainder of 1. Now, while it's true that we can continue on the process, assuming that we believe that decimals are legitimate, what is in fact the case is that when you do division, long division, and you obtain a remainder, when you obtain the remainder, you can actually stop because what your answer is actually technically equal to when we have 257 divided by 2 is we're saying that this is exactly equal to 128 and 1 part from 2. Where we got this 1 part from 2 as is we took the remainder, which happened to be 1, becomes the number in the numerator of our fractional part. So that's our remainder. And we divide it by the divisor, or however many parts you are cutting your pizza into. And so in this instance, we have a pizza with 257 slices. We're cutting it into halves, if you will. And so we should be able to get 128 pieces in each half with 1/2 piece left over. That's essentially what our answer is telling us here. It turns out that we can do a very similar process with polynomial division. And the reason we need to remember how to manipulate the remainders is that we're not necessarily guaranteed that we can divide a polynomial evenly across the expression. And so when we get to a problem where we need to use the remainder rules, we'll have to do just that. And we'll see what that looks like just in a second. But just like ordinary long division, what we're going to do is we're going to write our divisor term, which happens to be the 3x, or the terms that are in your denominator, out in front of this upside down or sideways L, where the quantity that is in your numerator, the 9x cubed minus 21x squared, that is going to be underneath the L itself. And what we're trying to do is we're going to try to ask ourselves, how many times does 3x go into the 9x cubed? Okay, so you're going to go over to the side of your page and you're going to ask yourself, how many times does 9x cubed, or it's rather, what happens when you divide 9x cubed by your 3x term? So at this point, you would have to expand your expression and you divide out your terms. Sorry, took one too many terms there. It turns out that 3x goes into 9x cubed. Let's see, x goes into x cubed an x squared amount of time, and 3 goes into 9 3 times. Or said another way, you look at the remainder of dividing the 9x cubed by 3x term. So you've got 3 times x, or 3x squared remaining. So now what you do with that remaining term is you're going to, just like before in the previous long division problem, you back multiply with whatever is out in front. And so now we're doing 3x squared times 3x, and x squared times x gives you an x cubed. 3 times 3 gives you 9. So when we get good at this, we're going to be very quickly be able to calculate the division process pretty easily, or fairly easily anyways. So now you divide 9x cubed with 9x cubed, and you get a 0x cubed left over. Just as before in the previous division problem, at this point in time, once you do subtraction, you're going to drop your term that's remaining. And so in this instance, we have a 21x squared term that's remaining. And remember, it's a negative 21x squared. And this is pretty critical because that negative sign is going to make all the difference in this instance. And we have to repeat this process. So 0x cubed is just 0. So just know that this 0x cubed can just cancel out. And you're just left with this 21x squared term. Now, what we're going to do is, just like before, we have to determine how many times does 3x go into 21x squared. And if we expand this expression, you'll divide out your terms and you see that you get a negative 7 and x. So said another way, 3 goes into 21 7 times because it is a negative 21. It needs to go a negative 7 times into negative 21. And then x goes into x squared, x number of times. So now we're going to, just like before, back multiply 7x, well, negative 7x rather, with the 3x. So negative 7 times 3 gives you a negative 21. X times x gives you an x squared. And of course, you're going to subtract this. Now, remember, subtraction of a negative is the same thing as addition. This is the tricky part. So put a star in this. This is the tricky part. Sometimes it's best to drop to the next line and do the calculation there if we can't remember. But subtraction with a negative is the same thing as addition. So now you will just add negative 21x squared with positive 21x squared. That gives you 0x squared, or 0 as your remainder. So what is the division of 9x cubed minus 21x squared with 3x? Well, according to this, because we have a 0 remainder, this will be equal to exactly 3x squared minus 7x. And that's all we have to do. Now, initially, this seems like a longer process, so students would, of course, be perplexed as to why would introduce a technique that seems to be much more involved than the previous two techniques that were mentioned earlier. But of course, the reason that we introduce these more complicated techniques is because in some instances, we may actually have to use those. We may have no choice because if you take, for example, 6x squared plus 9x minus 10, and we're dividing it by, say, 2x minus 1, there's no guarantee that we would necessarily be able to divide the numerator by the denominator. Okay, there's not any guarantee that we'd actually be able to perform this polynomial division operation. It's only because we were doing a monomial into this binomial or trinomial, and we were able to expand out or extract a GCF from the numerator that we were then able to, say, cancel out terms. And while there is indeed a very similar technique that we could use for, in this instance, this trinomial 6x squared plus 9x minus 10, i.e., we could try to factor the numerator expression, since we haven't discussed factoring just yet, we obviously don't have that technique that's available to us. And so instead, pretty much the only thing that we can do is we are going to try to use polynomial division. Because if we tried to extract a GCF from the numerator, there's no guarantee that the GCF would even divide out with whatever quantities in your denominator. And in fact, there isn't necessarily a GCF in this instance because you've got a 6x squared term, you have a 9x, and while you could extract a 3 from 6 and 9, you can't extract a 3 from 10. And while I could extract a 2 from 6 and 10, I can't extract a 2 from 9. So there really isn't a GCF in this particular instance. And so that's going to present a big problem to us. But one thing that we can do, if we remember polynomial division, is we're just going to write our divisor out in front, the 2x minus 1 term. And then underneath our division bar, we'll write out whatever's in our numerator, which in this instance is the 6x squared plus 9x minus 10. All right. Now, here's the tricky part, guys. We have to know exactly what we're trying to divide into this particular polynomial expression. And what we need to remember, what we need to be aware of is this idea that polynomials are always written in descending order because the descending order of a polynomial or descending degree of a polynomial is similar to the order of digits. So if you write, say, 105, we know that 105 means 100 plus 5, and this is not going to be the same thing as, say, 512. 1. The order of your digits for a specific number is very, very critical. Well, for polynomials, the order of the degree is critical as well. And so in a very similar manner as to, say, dividing a more complicated, say, 23 into 1,525, where you would take the 23 term and you would say, ask how many times it goes into 105. What we're going to do is we're going to actually use this highest, the term with the highest degree, rather, of your polynomial expression, and you're going to ask how many times it goes into the first term of the numerator, whatever the numerator term happens to be. So in this instance, we're asking how many times does 2x go into 6x squared? Well, for 6x squared divided by 2x, 6x is going to be 3 times 2 times x. And you'll have a 2 times x. And if you just divide out your terms, you'll see that it goes into it exactly 3x times. So you could write 3x, which makes sense because 3 times 2 gives you 6, and x times x gives you x squared. So now we can just go ahead and we're going to back multiply. But this time when we back multiply, we have to be very careful. We actually have to obey the distribution law. So we're going to back multiply and multiply the 3x with the 2x, which gives us 6x squared, which is all well and good. But now we have to remember to multiply the 3x with the negative 1. She should have a negative 3x here. And you're going to subtract 6x squared minus 6x squared. That's going to give you 0x squared. Negative negative is a positive. 9x plus 3x should give you a 12x. Remember, negative negative is a positive, so you kind of have to keep track of the signs in your head, or you could go back and you can erase the signs and rewrite the signs if you want to. But ultimately, you're going to have 0x squared plus 12x. And at that point in time, you can, let's see. Well, yeah, at that point in time, we can kind of drop the negative 10 if we want to. Okay, now we have to repeat this process over again. We're going to ask ourselves how many times does 2x go into 12x? So 2 goes into 12 6 times. X goes into x just once, so you actually don't have to write that. So we'll just have, whoops, my bad. Kind of having a wigging out here a little bit. So you'll just have a 6. 6 times 2 gives you 12. 6 times x gives you 12x. So, yeah, I'm sorry, 6 times 2x gives you 12x, rather. And then you'll have to multiply the 6 with the negative 1, so that gives you negative 6. And of course, you subtract. So 12x minus 12x gives you 0x. And negative 10 plus 6 gives us a negative 4. You just have to remember, negative and negative is a positive. So you're going to have negative 10 plus 6, which should give you a negative 4. So now you'll note at this point in time that 2x does not go into negative 4. So this is where we terminate. And you'll note that this is, in fact, our remainder of the expression. And so what this tells us is 6x squared plus 9x minus 10 all over 2x minus 1 is the same thing as 3x plus 6. And here's what we do with the negative 4. We're actually going to write that as a negative 4 in a numerator. And what do we write in the denominator of an expression? Well, we're going to have the 2x minus 1, or whatever happened to be the divisor of our expression. So you'll remember that a positive and negative is a negative, so we can rewrite this expression as 3x plus 6 minus 4 over 2x minus 1, and that is, in fact, the best answer. That's pretty much all there is to this particular chapter. Guys, you're going to be doing a bunch of division of polynomial problems in different ways. if you just kind of follow what we're doing here in the video, in the lecture video, you should be just fine. There's really not any surprises for chapter 5.5. Hope to see you guys in class. Take care.